if a real sequence an approaches A, then we want to prove that its arithmetic mean of the members of the sequence also approaches A, the same limit. You can use the precise definition epsilon n. So, special case, if A is equal to 0, I want to show that the desired sequence approaches 0 as well. So, given n epsilon, that's positive, can I find a capital N so that little n, when little n is large enough, can I show the following inequality? The absolute value of my desired sequence and 0 can be small enough. In other words, can I show that the A1 plus AN may not be, could be positive or negative, but anyway, absolute value, can it be small enough? Right? But, so in other words, so given n epsilon, given this epsilon, right? So from this epsilon, I derive half epsilon. I derive half epsilon. Arbitrarily given, once given, we fix it, right? So from this fixed epsilon, we derive half epsilon. And for this particular half epsilon, using definition of limit, right? It says for any positive constant, right? This can be close enough, right? So for this particular positive constant should also work, right? So in other words, I can already find a capital N1 that's large enough so that when little n is large enough, larger than this capital N1, then I can always have that AN is close enough to A. In other words, the absolute value of AN and 0, right, can be close enough, less than half epsilon, right? In other words, AN absolute value can be small enough, smaller than half of epsilon, as long as little n is large enough. So using this capital N1, I can split this one into two different parts. Right? So this A1 plus, first of all, using triangle inequality, this can be shown to be just less than n A1 absolute value plus all the way up to A sub N1 absolute value plus A n sub 1 plus 1, right? That's the next one after this. Plus all the way up to AN absolute value. Right? Triangle inequality. Then that is essentially n A1 absolute value plus all the way up to A sub N1 absolute value plus n A sub 1 sub N1 plus 1 absolute value plus all the way up to AN absolute value. Keep in mind, capital N sub 1 is fixed, right? So therefore, this sum at the top is also fixed. Maybe just that's denoted as capital M, right? Capital M fixed over little n, n approaches infinity. Keep in mind, this whole thing approaches 0. Now, when little n is large enough, right? Here, every member here, the subscript is already large enough, larger than capital N1. So, in other words, every single item at the top here is small enough, smaller than half epsilon. Right? So, in other words, this whole expression can be smaller than, again, denoted as capital M, the top, over little n, plus n. Every member is replaced with half epsilon. How many of them? Exactly little n minus capital N1. Many of them times half epsilon. Right. Again, fixed capital M over little n approach 0. But to write it in mathematics, we have to let when n is also large enough, larger than the floor of twice of m over epsilon, right? In that case, because somehow I let m over n to be small enough, smaller than, that's how I came up with this result, right? I let this be small enough, then I solve for little n larger than times 2 over epsilon, right? 2m over epsilon, right? That's where this comes from. Right? So this can be small enough, right? So overall, my expression can really be small enough, right? Smaller than half epsilon, and also little n minus capital N1 over n. Right? I subtract a positive constant from little n. Then if I do not subtract it, then it's going to be little n just over n, going to be 1. So after I subtract it, it's going to be less. It's going to be definitely less than 1, and also obviously greater than 0. So obviously between 0 and 1, right? So if I replace it with just 1, right, it's further loosened, right? Just half epsilon. So I've really shown that when little n is large enough, right? Not only larger than this capital N1, but also larger than this fixed positive constant. Right? So in other words, maximum of N1 and 2m over epsilon, absolute, the integer part. The larger one is my capital N, as long as little n is large enough. Then I've really shown that my desired sequence and 1, their distance, can be really shown to be small enough, smaller than epsilon. Right? So special case is proven. So when a is equal to 0, my arithmetic mean also approaches a, the same value. Now that I'm done with the special case when a is equal to 0, what if a is not equal to 0? In this case, or we can just simply construct a new sequence, Bn that's equal to An over minus A. An approaches A. An minus A approaches 0. Right? Bn easily approaches 0. Right? So Bn satisfies my special case. Right? When sequence approaches 0. Then the arithmetic mean also approaches 0. Arithmetic mean B1 plus Bn also approaches 0. Then what is B1? B1 is A1 minus A. Bn is An minus A. Now how many A's? N many A's. Right? Minus n many a's. And I also have a1 plus all the way up to an. Right? In other words, the limit of just a1 plus all the way up to an minus a is really approaching 0. In other words, we easily draw the conclusion that this limit actually easily approaches a.